Hello, my name is Kent Griffith, and I'm very honored to be presenting this work on niobium tungsten oxides for high-rate lithium-ion energy storage as part of the Charles Hatchett Award Seminar. It's particularly an honor to be the winner of the 41st Charles Hatchett Award, as niobium is the 41st element in the periodic table, and this is the international year of the periodic table. So along with my colleagues Camilla, Gianantonio, Lauren, and Claire, we published this work on the discovery and mechanistic study of some very interesting and promising battery materials based on niobium tungsten oxides in the journal Nature. And so I'd like to tell you about that work today and what we're doing in the future. So electrochemical energy storage is an area that spans many applications. We're all very familiar with the cell phones and the laptops that we use. You probably have at least 2 or 3 lithium-ion batteries sitting around you right now, a cell phone in your pocket and a computer on the table, but probably also many other household devices, things in your garage, power tools, and potentially an electric vehicle sitting in the garage too. And if not now, maybe in the next few years. And so we're really seeing this transition to battery energy storage worldwide. In Europe, most countries have set a date to ban the sale of new combustion engine vehicles. So in the UK, this is set to be 2040, with some more aggressive targets worldwide as well. And one of the big supports for this in the UK is the Faraday Institution to develop advanced batteries to really help create the materials needed to get us towards this electric vehicle and clean energy future. Along with that, we have an increasing proportion of renewables on the grid, and renewables such as wind and solar are intermittent. And so that means that we really need energy storage, at least in the short term, to be able to shift that load from the middle of the day when it's created to the evening, potentially some longer scale storage as well. And then we really have the focus on personal electronics, robotics, power tools, and a whole suite of new devices that are coming online that might have used to be static but are now part of this Internet of Things. So, I mean, everything is coming online, and many of those will be battery powered. And so we need an increasing number and also diversity of batteries to be able to meet all those needs. And so that brings us to where we are in the lithium-ion battery market. And so, right now we're sitting at around a $30 billion market, which corresponds to 160 gigawatt hours of battery energy storage. But this market, just for the lithium-ion market, is going to more than double in the next sort of 5 or 6 years, and then close to double again in another 5 years after that. So we're expecting to pass over 1,000 gigawatt hours before the end of next decade. And so this puts us in a situation where we need to think about coming up with advanced batteries for different applications. And so we'll jump into what some of these applications are and will be. So as I mentioned, we have intermittent renewables such as wind and solar, and these need a large grid scale size battery that can store and shift some of that energy load. We have an increasing number of electric vehicles, and these comprise a very relatively large battery to the size of the car. In some cases, almost the entire floor of the car is the battery pack, and it can also be one of the most expensive components. And so we need to think about ways to make these batteries cheaper, to last longer, to have increased safety, and to do things like charge faster. And that's where some of our work focuses. And so and then, of course, we go down to the scale of things like phones and laptops that we're much more familiar with. And we would all be happier if our phones charged in a few minutes instead of a few hours. And this is actually arguably more important in things like power tools, where we're moving to a cordless job site. We need to be able to recharge those tools rapidly during the day and not have to use them for 15 minutes and then leave them to charge for several times that amount of time. So we really need to be able to increase the battery power and performance, to do the jobs that we need to do, but also to keep those tools online for a higher proportion of the time. It's okay if our phones charge while we're sleeping, but we can't let our power tools charge while we're trying to do work. So now I'd like to go into what is inside a standard lithium-ion battery now, and what we're trying to change. And so in a conventional lithium-ion battery, well, in all lithium-ion batteries, we have two electrodes. We have a cathode and an anode. And these are the two components where our lithium ions and our electrons transfer between an electrolyte that sits in a separator. In the future, we might get rid of this separator component and move to a solid electrolyte. So rather than the liquid-soaked separator we have now, and that would increase the safety of the batteries, but we can actually change the electrode materials to move towards safer batteries too. And the electrode films, you can see an image of what a coin cell battery looks like deconstructed here, and that electron microscope image in the bottom left is actually what one of these electrode films looks like. So we zoom in there, and we're seeing individual particles that are in this case peeling off of a current collector where our electrons transfer through to go through the circuit and provide us energy. And in a conventional lithium-ion battery, the cathode that we would have is lithium cobalt oxide, if it's in something like most of our portable electronics. For electric vehicles and other applications, we're moving more towards nickel-rich versions of a similar crystal structure, but with nickel and manganese replacing most of the cobalt in the battery, in some cases aluminum. So these are NMC, NCA type batteries. But there are other cathodes as well. There's lithium iron phosphate for higher rate and for longer lifetimes, albeit at a lower energy density, and other cobalt-free cathodes like lithium manganese oxide, and some of the new rock salts based on manganese and niobium, for example. And our anode in almost every lithium-ion battery now is graphite. So graphite is good because it offers high energy density, and it operates at a very low voltage near lithium metal, which allows it to get the maximum cell voltage possible when paired with a cathode. But there are issues associated with that, and one of those issues is related to safety. So if we try and operate a conventional battery with a graphite electrode at a high current density, so we try and charge it fast or extract high power out of it, then there are risks to damaging that graphite structure. And in particular with fast charging, there are risks to plating lithium spindles or dendrites onto the surface, and those dendrites can actually short circuit the cell and lead to a battery fire or explosion. So there are real safety issues if we tried to charge graphite too fast, and so there are engineering controls that currently prevent you from doing a 5-minute charge. But if we could develop new materials that enabled us to do that, we could eliminate those safety issues. Now, there is a small couple percent of the market currently which does utilize a material for high power and for fast charging applications, and that's the lithium titanate spinel. And so this material has a much higher voltage than graphite, and being the anode, that means that it has a lower cell voltage, and so we get less energy out of an LTO paired with any cathode that we use versus pairing it with graphite. And there's also a limited capacity that comes out because we're not taking full advantage of the transition metals that we have present, only utilizing the redox capacity of 3/5 of the titanium. And but because of this metal oxide crystal structure and because of the voltage it operates at, it's very safe, and it has a long cycle life. So over 10,000 cycles can be achieved with LTO. There is one other caveat, that because it has limited lithium and electron transport, the particles do normally need to be nanoscaled to access these high rates in order to get the particles fully lithiated or delithiated, again in a sort of minutes time scale. And so even though the market share of this is small, at around 4,000 tons a year and say 3 or 4% of the market, it's growing very rapidly because there is an increasing demand for fast charging applications and high power batteries. So we're seeing a 25% growth every year and expecting 50,000 tons in just about a decade of these high rate anodes. So there's clearly a demand then for high rate anodes, and would be even larger for new materials that have advantages in terms of energy density or in terms of temperature operating condition, one of the other variables that can exceed the performance we have now for fast charging batteries. And so one such material is being developed by Toshiba, and that's the NTO titanium niobium oxide which has a crystallographic shear structure. And we're going to get into what that is because it actually relates to the niobium tungsten oxide batteries that we've been studying as well. And so, the work that I'll be presenting today that we were awarded the Charles Hatchett Award for this year is based on the discovery and characterization of lithium-ion battery materials comprising two different niobium tungsten oxides. But all of this work stemmed from a more fundamental initial study on NB205. And so I'm going to start here with the lessons that we learned on NB205. And the crystal structure I'm showing is called a Wadsley-Roth structure or a crystallographic shear structure because it's made up of blocks that are ReO3-like. And so on this inset in red, we have the ReO3 structure, which is perovskite without the A-site cation. And this ReO3 structure is perfectly corner sharing. But in NB205, we don't have that 1:3 metal to oxygen ratio required for perfect corner sharing. And so there are different ways that the defect chemistry could adopt to overcome this, but in the shear structures, those planes shift with respect to one another, and so you go from fully corner sharing to some edge sharing sites. So the structure effectively condenses into blocks, and these blocks can take different sizes. So in the polymorph of niobia, we have two different block sizes, and actually it doesn't. This structure type doesn't just occur, though, in pure niobium oxides. So like in the titanium niobium oxide that Toshiba's working on, most of the early transition metals and some things further abroad in the periodic table can actually be incorporated. You can change that metal-oxygen ratio, and you can get different block sizes, different arrangements, and different structures based on this crystallographic shear motif. And so in our case, we took what we learned about this to explore a whole series of these compounds. And the one that I'll be focusing on today as the most promising from our studies is the 16,5 niobium tungsten oxide structure, which has, because of the inclusion of around 25% tungsten, it has a larger block size. So there's more corner sharing, but you still have these shear planes leading to 5x4 blocks. Now, in addition to the crystallographic shear structures, if you go towards a more tungsten-rich chemistry, closer to 1:1 with niobium, then you actually form a crystal structure that looks bronze-like. And this is very reminiscent of what we see in a low-temperature polymorph of niobium oxide called TNB205. And so TNB205 itself shows some promising battery performance, somewhat limited capacity, but is a very interesting material. And we actually then can see the comparisons between that and this niobium tungsten bronze. And so if we think about how we get there, NB18W16O93 crystal structure is really a bronze derivative of the tetragonal tungsten bronze. And so we can envision how that analogy plays out here. So in the tetragonal tungsten bronze, we have partially reduced tungsten, which forms a corner sharing octahedral network that's stabilized by some intercalant, say potassium in this example. And if we imagine a supercell of that tetragonal tungsten bronze, we can see the sort of parallels between that distorted corner shared network and the blue distorted corner shared network in the NWO bronze. The difference here is that rather than having a stabilizing and reducing presence of something like potassium, we actually place some of our niobium and tungsten atoms into those tunnels and form these pentagonal bipyramidal tunnels that stabilize the structure inherently. And so that means we start with a fully oxidized network, and we can get the maximum amount of capacity out of our structure from the time that we start lithiating. And so once we understand something about the atomic scale structure, then it's also important to think about what our microstructure is like. And so conventionally, when we're working with high rate materials or trying to do very, very fast charging, fast lithiation and delithiation, we think about going to the nanoscale because we decrease the diffusion distances required. But there are some disadvantages with going to the nanoscale in terms of our ability to cost effectively synthesize the materials and process them and reactivity down the line. And so here we are studying large micron scale particles, sort of the 3 to 10 micron range, fully dense non-porous materials, and we actually observe that they show the extremely high rate performance that we would conventionally only be able to get out of a nanostructured version of something like LTO. And so this gives us several advantages. It has advantages at the material synthesis level, because these powders are easily scalable, from the lab scale up through commercially relevant, kilos to tons. And there's a low manufacturing cost associated with that because we don't have to do any complex hierarchical or nanostructuring to these materials. And as a side note, conversely to LTO, this is a lithium-free synthesis. And so we avoid the issues with lithium volatilization and getting those lithium contents just right at the high temperature synthesis of LTO. And so that makes our material synthesis a bit easier and cheaper. There are also electrode manufacturing advantages of using these bulk materials because nanomaterials can be hard to process. They can be hard to dry due to the high surface area and affinity for water. And just seemingly simple things like powder mixing and slurry coating can be challenging, whereas with these large bulk micrometer particles, we can use completely standard industrial processing of them. And then finally, once we actually get to a fully formed battery, there are significant advantages to having micron scale particles because we'll have a much lower surface area of our active electrode material in contact with our electrolyte. And so that means that we should have a low reactivity, minimal gassing and SEI formation, and these will lead directly to things like long cycle life and high safety. And we're enabled to do this only if we have a very fast diffusion such that we can get through, say, 5 or 10 microns of material in a matter of a couple minutes to do full lithiation and delithiation of these particles and access our maximum capacity. And so to jump into that electrochemistry then, we're looking at here the crystallographic shear structure. And so on the left, there's a plot of the discharge and charge curves and a differential plot next to that on the right where we can try and envision where this charge is being stored. So we're in the range of mostly between 1 and 2 volts. And the average voltage of these materials is actually almost identical to LTO, around 1.55, 1.6 volts versus lithium. And so here we're looking at this as a function of rate, going all the way from a 5-hour charge discharge up to a less than 1 minute charge or discharge half cycle. And so we can see that there's a relatively weak dependence on rate, where even at say 10C or 20C, which corresponds to 6 to 3 minutes for a charge or a discharge, we're able to access almost 150 milliamp hours per gram and nearly a full lithium and electron transfer for every transition metal we have present. So for every niobium and tungsten, we're getting at least 1 lithium and electron out. And at lower rates, we're actually exceeding that significantly, which means there must be multi-electron redox chemistry happening. So either our tungsten and or our niobium is providing us with multi-electron redox capability, a question that we definitely want to explore a little bit later on. And in the bronze structure, now the details of the discharge curve are different, and again raises interesting questions about what the differences in this material are, but the net electrochemical effect is very similar. We have an average voltage around 1.6 volts, and we're getting similar capacities out, including multi-electron redox from something in our niobium tungsten oxide. And one of the things that we noticed in these is that if you look at the initial part of the discharge curves, for either material, we have a large overpotential that's bringing down where we start lithiating. And so we wondered about the nature of this overpotential. So these materials, these niobium tungsten oxides, were tested in half cells against lithium metal. So we wanted to see what the effect of the lithium metal was, because you can't truly independently test a single electrode. And so we made lithium-lithium half cells, which is this plot that I've superimposed in the top right here. And what we observed was that at the current densities that correspond to our high rate measurements, say 10C, 20C, we saw an identical overpotential in the lithium-lithium half cells. So we believe that overpotential is coming from something in the process of lithium and plating and stripping and the associated ion transfer for those reactions. And so actually we're not necessarily pushing or observing the limits of our NWO materials. We're observing the limits of a cell as a whole, and these could well be coming from the lithium metal process. Now, if we look at that data In summary here, these little dotted lines are showing us where the theoretical 1 electron reduction capacity corresponds to. So it's around 150 to 170 milliamperes per gram for the two different materials. And what we see, though, is at 10C, so 6-minute charge or discharge, we're accessing the full 1 electron theoretical capacity. And then anything slower than that, we're actually doing multi-electron redox chemistry. And so we wanted to test what the durability of these were as well. So we did 1,000 cycles, 250 at 10C and 750 at 20C, and observed only about a 5% loss in capacity over 1,000 cycles, indicating a projected cycle life, of many thousand cycles for these materials, but inherently indicating that these bulk micron structures are stable to full charge-discharge lithiation at very high rates. And so that's an inherent advantage they have over graphite as well, in addition to being safer, doing these high current density charge and discharge. They're able to do it without losing capacity. And so if you try and do even moderately fast charging, supercharging, things like that in your electric vehicle now, it does cause some degradation to the battery and will lead to a shorter expected cycle life. So you won't be able to discharge as many times. But with these advanced oxide anodes, we don't see any of that degradation. So not only should it be safer, but we should be able to do it for many thousands of cycles and get a much longer lifetime out of our batteries. And so comparing that to everything else out there, even very small nanostructures of things like TiO2, different versions of LTO, different hierarchical complexes with carbon nanostructures and porosity, all of these things. These niobium tungsten oxides compare very favorably. They have a very high volumetric energy density, thanks not only to their inherent crystallographic density, but then also this microstructural density where we're using bulk dense particles. And so what that means is we can pack a lot in a small space, and for volume-constrained applications, which applies to many, many things. So the electric vehicle manufacturers tell us directly, quotes from Ford say that they care about volumetric energy density. This is the focus. This is what we have to maximize, because there's a defined space in this vehicle in which to put a battery, and we need to fit in as much as we can. And a similar trade-offs are made in many other applications. Personal electronics and power tools, of having a defined volume and needing to be able to fit in the maximal capacity. And that's really where our materials shine. And so if we look at this in a Ragone plot where we're comparing energy density and power density, what we find is that because of the high density of these particles, high volumetric densities, we're able to, over a wide variety of rates and powers, supersede even the best materials out there in terms of other nanostructured metal oxides, and also, of course, conventional lower rate materials like graphite, which fall off very rapidly as you approach high power densities. So once we had a handle on the electrochemistry and we observed the performance of these materials, we really wanted to get a better understanding of why they behave this way. And so we went to do chemical and structural analysis with a suite of advanced characterization tools, many of these being based at synchrotron X-ray sources in the UK and in the US. And so what I'd like to talk about first is the ex situ X-ray absorption that we did at a diamond light source. And this was with the principal beamline scientist there, Gian Antonio Sivan. And so X-ray absorption spectroscopy is a local structure technique where we're actually able to individually look at, say, the tungsten or the niobium in our materials and try and learn about how these, the chemistry, so the oxidation state of these is evolving as a function of state of charge, and also look at how the local structure, the local symmetry is evolving as a state of charge. And so we did this individually, and in this plot on the right, you can see that we should expect a shift in the absorption edge as a function of the oxidation state. So from niobium 5+ in Nb2O5 all the way to niobium 0 in niobium metal, we see about a 20 eV shift in where that absorption occurs. And if we are able to map over the niobium and the tungsten individually, as a function of state of charge, we can see which one is being reduced where and which one of them is leading to the excess capacity that we observe in these materials. So XAS is a great element-specific technique that we can discriminate between the performance of these two metals, and we're sensitive to the bulk structure. So we're seeing the whole particle, which complements surface-sensitive techniques. But in XAS, we really want to understand what's going on in the bulk. We're probing not only the electronic structure in the oxidation state, but also, as I mentioned, that local atomic structure. And so in this example here on the crystallographic shear phase, and there are analogous data for the 1816 bronze, what we see is that as we move down a function of so discharge in the half cell, so this is lithiation, as we increasingly lithiate the materials, we're moving from D0 niobium and tungsten nominally to D1, and then in our multi-electron redox even D2 electron counting. And so that should be associated with an edge shift, which we observe. And the other subtlety in these materials is that when they're D0, they experience what's called a second-order Jahn-Teller effect. This second-order Jahn-Teller effect occurs when there's a pseudo-degeneracy between the filled p orbitals and the empty d orbitals in these early transition metal oxides. And so this gives rise here to a pre-edge feature because the second-order Jahn-Teller distortion causes an off-centering of the transition metal. And this off-centering then has implications for the long-range structure of these atoms as well. But what we observe is that as we reduce our transition metals, we should see a removal of this distortion and therefore actually an increase in the local symmetry of our octahedra, so becoming less distorted. And also that should be correlated then with a decrease in our pre-edge feature. So we use that as a separate measure of the reduction of each of these transition metals and an observation about the local symmetry. So we're actually observing our octahedra becoming more ordered and less distorted as we lithiate these phases. And so those data are shown here. On the left, we have the niobium oxidation state. In the middle, we have the tungsten oxidation state independently from that tungsten X-ray absorption data. And on the right, we're showing the pre-edge peak intensity, so that pre-edge feature that comes from the second-order Jahn-Teller distortion. And so when we look at this together, what we see is that both the niobium and the tungsten are reduced in parallel, not sequentially. So they're both fully participating in the redox process at all states of charge. And they're both participating in multi-electron redox. So as we get up to high amounts of lithiation, so above 1 lithium per transition metal, we are still seeing reduction in both the niobium and the tungsten. And the pre-edge peak intensity, which is again an independent measure from the shift in the absorption edge, tells the same story. It says that both the niobium and the tungsten are being reduced at all states of charge. Those octahedra are becoming more symmetric, and that this is occurring roughly linearly between the two transition metals, with a slight preference for tungsten reduction initially, and we observe that also in the slight increase in our anode voltage as we incorporate more tungsten. And once we understood this local structure picture of how our individual octahedra were being affected by lithiation and what was being reduced, where our oxidation chemistry was coming from, we were also interested in how the overall lattice was responding. And so we did some operando high rate diffraction at the Advanced Photon Source at Argonne National Lab near Chicago. And this was work with beamline scientist and chemist Camilla there. And so what we did was we used the Ampix cells that they developed, which is an invention of the Advanced Photon Source, in order to perform high-rate electrochemistry in the presence of an X-ray beam and get the same observable electrochemistry as you get in the conventional coin cells that we test in our lab. So we want to be sure that what we're measuring in the X-ray beam is the same as what we would be measuring in the lab. And so we do that here. And the other advantage then of going to a synchrotron like the APS is that we're able to collect a diffraction pattern every couple of seconds. And so that means we can actually measure real-time high rate, charge-discharge cycling in, say, 6 minutes, and we can record hundreds of diffraction patterns in that time, and then be able to get this really precise look at how that atomic structure is evolving. And so what we see in the crystallographic shear structure, and is seen in other crystallographic shear structures as well, is that there's a three-phase evolution. So initially that block that we have, our blocks of our Wadsley-Roth phase, start expanding, and then in the middle stage they contract. And they actually contract to smaller than where they started, which is relatively unique, that as we're adding atoms to the system, as we're lithiating, part of our structure is contracting in response to this. And then the layers of those are monotonically expanding. But because of this anisotropy between how our lattice is evolving, we have an overall small volume expansion. And this small volume expansion is great because it minimizes the strain on these particles. And that also allows us to use these large sort of 5-10 micron particles without observing significant cracking or things over thousands of cycles. When you fully lithiate something and have a large volume expansion, so say in the case of silicon as an advanced anode material, which has a several 100% expansion in its volume compared to the 5% we're observing here, then you get significant cracking. And that particle cracking makes it very hard to stabilize the structures for many cycles, which is important as we're trying to achieve many thousand here. Now, the structure evolution is very different in the bronze phase. We have a 6-phase at least structure evolution as we lithiate, and we even have a very small 2-phase region, but we don't observe any kinetic slowdown effects as we go through this very small 2-phase region. So we just have a lithium miscibility gap, maybe in how much lithium can be in this phase before it swaps. But the overall mechanism of having an anisotropic volume expansion is so strong in this structure that actually, as you go from about 50% state of charge down to fully lithiated, the whole volume of the structure contracts. And so this leaves you with a fully lithiated Li34 NB18 W16093, which has only about a 2.5% volume expansion. So very, very small volume expansion, which is certainly going to be helpful when we're trying to cycle these structures thousands of times without having degradation and cracking. And so from that point on, we had this information in hand about the local structure, something about how the lattice responds. And we really wanted to get some information on the dynamics and understand what the kinetics of the lithium are inside of this. And it's challenging in an electrode material because you have electrons and ions carrying charge, whereas in a solid electrolyte, you nominally only have ions carrying charge. So that means in an electrode material, which is a mixed ionic electronic conductor, you really have to find a way to separate these two components. So measuring charge is not necessarily going to be easy to interpret what those charge carriers are. The big advantage of pulsed field gradient NMR spectroscopy is that you're able to look specifically at the lithium ions and nothing else. So the contributions we're seeing here, even in a mixed conductor, are coming purely from lithium motion. And it's a direct way to measure the diffusion of this material. So in the bottom left here, we've got a conventional NMR spectrum of our lithiated niobium tungsten oxide. And what we do is we apply we pulse the field gradient on this. We give it some time for the lithium ions to move, and then we refocus and remeasure that signal. And so basically, the more that those lithium ions are moving, the more the signal is going to dephase and to move further through experience a different field. And so we'll expect the intensity to decrease. And so that's what this graph in the bottom left shows, is that as we increase the gradient strength, we have less and less intensity. And we can do this as a function of temperature. We can do this as a function of state of charge. And we can try and work out what the diffusion coefficients and the activation barriers for lithium hopping between the different sites would be. And so in this case, we find that the room temperature lithium diffusion is something around 10 to the minus 13 meters squared per second. And it's characterized by a pretty low activation energy barrier of 200 to 300 MeV. This was all work that was pushed by Lauren Marbella in our group, who is now an assistant professor at Columbia University, carrying on the development of PFG NMR methods. Now, so getting this information out was really useful to understand why we're able to lithiate these large particles in a small time scale, but we need to put these numbers into context. So what does it mean that we're at 10 to the minus 13 meters squared per second? Well, what it means is that we're only, an order of magnitude or so off of the lithium diffusion in a liquid electrolyte. And similarly, we're about on par with the best lithium diffusion in single conducting solid electrolytes. And if we compare that to other electrode materials, things like graphite or LTO or some of the cathode materials, we're sort of 2 to up to sort of 6 or 7 orders of magnitude faster diffusion than you would see in common mixed ionic electronic conducting electrode materials. And so if we think about the implications of that, you can see in the top left here, this is just a sort of back of the envelope calculation of what diffusion distance we would expect in a given amount of time for a given diffusion rate. And what we see is that, if you want to do 20C charge-discharge of your battery, then in order to do micron scale diffusion, you need to be at least 10 to the minus 14 meters squared per second for your diffusion coefficient. I'll remind you that we're at 10 to the minus 13, so we're an order of magnitude higher. So that puts us in the range where we would expect to be able to get something like, again, 10 or so microns in our 20C rate, which perfectly correlates with what we observed in the electrochemistry. And again, if you put in the numbers that you'd get for something like LTO, then it should be pushing down into the nanometer scale in what you would be able to fully lithiate and delithiate just because of the inherent diffusion coefficient. So this is really the criterion that's necessary in order for the structure to lithiate this fast. And so some of the work we've done since then is trying to use DFT electronic structure calculations to provide further insights into how the electron transport is going along with the ion transport in these materials. And so this is work by John Koser and Andrew Morris, our close collaborators. And so what we found through these electronic structure calculations is that in these crystallographic shear structures, there are sort of 2 different types of metal cations. There are the ones that are in the center of the blocks, and there are the ones that are along the crystallographic shear planes. And what we find is that the one in the center of the blocks, they sort of hold electrons more tightly and have localized behavior. And the ones along the shear planes have overlap that provides for metallic conductivity once we've lithiated these materials. And so these crystallographic shear planes that run orthogonal to each other actually provide a totally interconnected electronic conduction pathway that goes along with our rapid lithium ion conduction. So putting these 2 things together provides exactly what we'd need for high rate lithiation of an electrode active material. So if we take all of this together, we're really starting to get an understanding of what the mechanism is of this high rate lithium intercalation leading to rapid energy storage in the niobium tungsten oxides. Now, the structures of the 2 phases are quite different, but they have some common themes. And the thing that really provides the structural stability is this, what I'll call a frustrated polyhedral network. So in the crystallographic shear structures, they've got the shear planes that prevent the sort of twisting and tilting that you would expect in a perovskite structure if you tried to put lithium in, which would clamp down and really decrease the rate. And in the bronze structure, there are these locked pentagonal tunnels that, again, prevent you from having structural distortions that would be harmful either for cyclability or for rate. So these things maintain an open diffusion pathway, something like a room and pillar network in the bronze structure, where you keep these 2-dimensional open spaces and even have some additional 3rd dimension through the empty tunnels. And then this down block diffusion, sort of like a multi-lane highway, where lithium ions can hop between different openings in the block and go rapidly through the open structure. And then the other thing, of course, is that we have the multi-electron redox coming from both the niobium and the tungsten. So that really allows us to push how much capacity we can get out of these materials. And so now we're taking that further and translating this into full cells. For high energy density full cells, we would pair it with a nickel-rich NMC cathode. And for the optimal lifetime and perhaps rate, we would pair it with a lithium iron phosphate cathode. And so in our initial studies of these using thicker electrodes and full cell studies, we're able to see that we can get close to 90% capacity retention for about 10-minute charge-discharge and 500 cycles with the high energy density cells. And we're at about 90% capacity retention, even over 1,000 cycles and 6-minute full state of charge-discharge with the lithium iron phosphate. So we're really excited about these initial full cell results and optimistic that we can push these materials forward and translate them into full commercial batteries that can meet some of the demands of our next generation of energy storage needs for a wide variety of applications. The other thing that we've seen is that like in the half cells with lithium, in these full cells, we're observing higher impedance from the cathode, not from our NWO. And so we still think there's optimization to be done away from our active materials to really get the maximum full cell performance. So with that, I would just like to thank all of my coworkers on this and my funding sources. So Professor Claire Gray, who directed this work, Lauren Marbella, who is a fantastic help measuring these lithium dynamics with the PFG NMR. Beamline scientists Camilla and Gian Antonio, as well as people who I've worked with on the niobium oxide projects leading up to this. So Anatoly, John, and Alex were all there along the way to understand these fundamental insights on mechanisms in niobia that led to these mixed transition metal oxides. And then all of our theory collaborators. So John's really leading that work under Andrew Morris, and my funding sources. So Churchill Scholarship, which is what brought me to Cambridge in the first place, and then the funding that supported my work there, and also traveling to beamlines around the world. So the Herschel Smith Scholarship, the Cambridge Trust, and STFC Batteries. Thank you very much.